Good morning and happy Tuesday. Today is Tuesday, March the 31st, and hopefully today is the last day of our remote learning adventure. In any event, today we are going to continue on with the third lesson in our series or unit on electricity, lesson number 74 according to the numbers here. And this is about what we call electric fields. Now, let me give you an analogy. All right, when we talk about a planet or a star, all right, we talk about an area surrounding that star or surrounding that planet as having a gravitational field. Right? For example, the Earth is held within the Sun's gravitational field. Pluto and Saturn and all the other planets are also held in the Sun's gravitational field. The Moon is held in the Earth's gravitational field. This is because the force of gravity causes those objects to gravitation to be attractive. All right, and by the way, gravity is of course an attractive force, whereas electricity can be either attractive or it can be repulsive. So, same kind of concept deals or surrounds a charged particle. All right, so an electric field exists whenever an electric force acts upon a charge. So if you have a charged particle somewhere, it's got a big old positive charge, all right? Well then, everything surrounding that object that's got a charge on it will be either attracted to or repulsed by that object, all right? And so the big old positive charge, all right, that's going to attract all the local negative charges, and it's going to repel all of the local positive charges. All right. Now this field exists around every single charged object that exists in the universe, just like gravity exists. A gravitational field exists around any object with mass in the universe. All right, and so this electric field is something that we really need to pay attention to, because you'll remember from yesterday's lesson that the universal constant, Coulomb's constant, is actually 20 orders of magnitude greater than the gravitational constant that Newton identified. Now, electric fields are vector quantities, and they are defined as the direction of force on a positive test charge. This is important, okay? On a positive test charge placed in the field. So let's say that my fist represents a positive charged particle, and my little finger here represents a positive test charge. Well, if both of these things are positive and the point charge is stationary, what's going to happen to the test charge? Well, it's going to be repelled, and it's going to go away. Okay. On the other hand, if I've got a positive point charge sitting there right in front of my big ugly mug, and I put a negative point charge or test charge out here, all right, what's going to happen? Boink, is going to be attracted. Okay. So the direction is very important here. So we define an electric field as a vector quantity defined as the direction of force on a positive test charge. So what happens when I put a little positive charge near this other charged particle? Will it be attracted or will it be repelled? So this brings us to a description of electric fields. And if we were in our classroom and on the smartboard, I would attempt to draw this with a point charge here and that sort of thing. I will show you the drawings when we get back to school, or you can have a look at the Mr. Anderson video at the end of this PowerPoint, and that hopefully will kind of clarify it a little bit. Unfortunately, with the tools that I have available to me here at home, I'm not able to actually draw on this or in this video. So that brings us to our next little slide here. When we deal with electric fields, there is some arithmetic involved. All right. It turns out that you can calculate the intensity of an electric field based on a couple of factors. All right? I don't know why those factors aren't. There we go. So the intensity of an electric field, which is defined as a capital E, all right, for electric, is defined as E equals F divided by Q, okay, where F represents the force, the electric force, and Q represents the charge of the particle that we're dealing with, all right? So it can be positive or negative, so keep that in mind as well. All right, E equals F divided by Q. This formula is found on the electric page of your handy-dandy New York State reference tables, so have a look. This brings us to example number 2, all right, dealing with electric fields, electric field intensity, forces, and charge. So let's start here. Calculate the force exerted on an electron in an electric field whose intensity is 2.0 times 10 to the 2th newtons per coulomb. Okay, so we're looking for the force. We've got an electric field with an intensity of 2 times 10 to the 2th newtons per coulomb, and on an electron. Now, notice we got 3 variables in this formula, but there's only one number in my example here. It turns out that this word electron is very important here. All right, and the reason that it's important is because we know what the charge on an electron is. Every electron, and proton by the way, has a charge of 1.60 times 10 to the negative 19th coulombs, an elementary charge. Remember, 1Q, one elementary charge, is 1.60 times 10 to the negative 19th coulombs. And again, you can find that on the front page of your handy-dandy reference tables. So, how do we go about addressing this example number 2? Like every other problem that we've done so far this year, we start with the laundry list, okay? So, come on laundry list, there we go. So, obviously force is our big fat question mark. That's what we are looking to calculate in this particular case. And so that's where we'll start. F equals big fat question mark. All right, secondly, we know that the charge is the charge that you find on an electron. Now, I actually just realized I made a mistake when I typed this up this morning. Q should be negative 1.60 times 10 to the negative 19th coulombs. Okay? The electric field intensity, E, is 2.20 times 10 to the 2th newtons per coulomb. And here that pops up right now. All right, so how do we actually calculate this? Well, in our next step, we're going to write down the equation here. E equals F divided by Q. And notice the units match here because the units for electric field intensity are newtons per coulomb. The units for force are newtons, and for charge are coulombs. So that makes perfect sense, newtons per coulomb. At this point, we can simply plug and chug. The electric field intensity, therefore, is going to equal, we're solving for force. So I rearranged this equation algebraically. F equals E times Q. Therefore, 2.0 times 10 to the 2th newtons per coulomb times negative, remember I made a mistake there, negative 1.60 times 10 to the negative 19th coulombs, and I get a force of negative, and I think I made the same mistake here, negative 3.20, negative 3.2 times 10 to the negative 17th newtons. Okay. Now, in terms of calculating electric field, whoa, that all popped up at once. One of the things that I do want you to understand is that the formula over here on the right, E equals F over Q, is the one we just talked about. But remember that the electric force, F, is equal to K times Q1 times Q2 over R squared. If we combine these two equations, we can get another equation for electric field intensity, where it's equal to K times the charge on the object divided by the distance between that object and the point charge. Okay? Now this formula is one that I think that you should know, but it is not included on your handy dandy New York State reference tables. All right, so I would suggest that you write that down somewhere. Now, this is for a point charge and a point charge only. We're going to talk about parallel plates where one plate is positive and one plate is negative a little bit later on. But I just want you to keep in mind that the electric field intensity for parallel plates is constant always. Now, notice that the relationship between electric field intensity and distance, this should have been a smooth curve. It didn't come out to be a smooth curve, but oh well. But again, it illustrates the inverse square law that we talked about yesterday. Now, that brings us to example number 3, which is a question designed to work out the using the new formula that we just derived. What is the intensity of the electric field 0.0040 meters from a positive charge of 3.20 times 10 to the negative 19th coulombs? All right, so we're looking for E. We've got a value of R, which is 0.0040 meters, and a value of Q, which is 3.2 times 10 to the negative 19th coulombs. So here we go. Example number 3. Okay. Once again, we begin with our laundry list. The electric field intensity, E, is going to be the big fat question mark in this case. And so here we are putting or writing that down. Now, we know that the distance here is, or between the point charge and the test charge that we're dealing with, is 0.0040 meters. We know that the charge on the point charge that we're dealing with is positive 3.2 times 10 to the negative 19th coulombs. And of course, we know the value of Coulomb's constant is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Excuse me. No corona, I promise. Now, in this case, we simply write down the formula that we derived in the previous slide. E equals K times Q over R squared. In this particular case, because we are trying to solve for E, there is no reason to rearrange this formula algebraically. And so we can simply plug and chug. Now, I have not included the units in this measurement, again, because there's not enough room on the slide here. But 8.99 times 10 to the 9th Newton meters squared per Coulomb squared times 3.2 times 10 to the negative 19th coulombs divided by 0.0040 meters squared leaves me with a value of 1.8 times 10 to the negative 4th newtons per coulomb. Okay. All right. Now, here is a hyperlink to a Mr. Anderson video on electric fields. I have uploaded the PowerPoint here. I don't know that you can directly link through this video, so please make sure that you download rather the PowerPoint and link to this video and have a look at it, or just copy it into your browser. And finally, my friends, your homework for tonight, which hopefully I will collect tomorrow, is to do questions 3 and 4 on the electricity homework sheet. Okay? Questions 3 and 4. All right? All right, my friends, have yourselves a lovely day, and I'm praying that I get to see you tomorrow. Bye-bye now.